right, I'm going to go ahead and get started. Let me clear this up. All right, move these robots out of the way. All right. Okay, so this stream is going to be the first part in a series that I was asked to do by several people on Reddit to describe how to build these little robotic armigers. These are made completely out of, well, not completely out of GW plastic from the Armiger models, but very, very similar. Uh, the model, I'm going to go ahead and turn this guy off so he stops thrashing around. And so I don't get poked in the eye by a laser, because you guys have lasers. These little things right here, lasers. Yeah, you can do all sorts of really stupid stuff with these. All right, so what I'm gonna describe how to do is just kind of build one of these. This one is a bit more sophisticated than what I'm gonna build on the stream here. Uh, this one uses 3 servos, and for a model of this size, it's rather complex. It's got voltage converters all over the place. It's a bit laser power boosters inside. It's a bit more sophisticated than I think would make a good starter project, but it's not far off. So if you watch the stream and you want to know how to build this or something like this, I'll get you the knowledge you need to do it and show you the basic methods for it, and you can take it from there. Because really, what we're going to build in these streams is it's like the little brother of this one. It'll have one servo, some LEDs. It'll move the torso. But from there, once you understand how to do this, how to the principles, how we build the base, which is what we're going to do today. You can take this base and use it to build a project like this, where you've got multiple axes of motion, lasers, power conversion, all this crazy stuff inside this guy. It's going to be using the same base that we're building today. Inside here, we've got, I don't know how well you can see this, but you've got your battery, your voltage converter, your microcontroller. It's right here, kind of broken off. And yeah, you've got your Wi-Fi antenna, all your wiring, a power switch. This stuff looks complicated, but it's really not that bad. I tell people, when I learned to build these things, I knew nothing about robotics. I knew nothing. I knew about electronics to some degree, but not like this. So, if I can learn to do this, anyone can learn to do this. As long as you've got the interest and some money. Yeah, it does definitely take some money, because these things aren't cheap to build. But yeah, the interest and the drive, and just the willingness to learn. Get those things taken care of, you're all set. So basically, I want to go over this thing kind of like base to the tip or the top, and I'll show you what these things are made of. Like I said before, the one that I'm going to build in the stream here is not going to be quite as sophisticated as this one. The one we're going to build, I'm going to show you 2 different versions of this. The one you can see there's a servo. Let me turn it around here. You can kind of see that there's a servo right here. This replaces the like the pelvic joint that would be on the normal GW model. It looks, it fits in pretty well. You can see he's got a bit of junk in the trunk, but we're going to build one. I'm going to show you how to build one with the servo outside of the body and one with the servo inside of the body. Both of these designs have their uses. You build the one, like I like building them with the servo in the hip to turn the waist, because that allows you to do a lot more, to jam a lot more in the hollow space inside the torso. So if you wanted to, put some, additional motors like this guy, they're very hard to see, but you've got servos in the shoulders here. Those are mostly housed inside, but they stick out. And this is custom designed. These side panels are custom designed, 3D printed panels that mount the servos on the outside. Not going to do that right now because there's some iffiness with providing STLs for GW reproductions of GW plastic. I don't want to get into any of their legal scrutiny. But the ones that I'm going to build, and I will provide all the STLs for these. We'll have one servo in the base, either in the hips or inside the head. That will allow you to design a robot that can do torso twists like so. And I'll also be showing you how to put LEDs that you can control the brightness of with the microcontroller in the base. And the great thing about these is because the microcontroller in the base is designed for hobby uses, you're just using the coding for it is all in Python, which is quite possibly the easiest programming language I've ever learned, and it's excellent for amateurs because it's very forgiving in how it works. Additionally, all of the electronics in this are sold by a company called Adafruit, which is very, very good about providing documentation for how everything works, tutorials, whatever you need to get started. So these are surprisingly easy to build if you're willing to put in the time and the effort, because these things do take a lot of effort to build, a lot of time to build, and they're not exactly the cheapest thing either. I'd say to build something like this, if you already have a 3D printer, you've already got that set up, you got the model kit, which is probably like $80 or $90, which gets you two of these guys. And then you've got the power boost converter inside, the battery, the microcontroller, the servos, the wiring, the LEDs. You're probably looking at an additional, depending on what you use, about maybe $50 to $100 on top of the individual model. You can do it cheaper, of course. There is no single right way to do these. But by no means am I ever going to imply that anything I'm building here is a single source of truth, the right way, the wrong way, whatever. These are just the way I taught myself to build these. So if you have any, you could definitely improve on the design, whatever floats your boat. I encourage it. And as I said, I'll be providing the STLs that I use for the 3D printed parts and all the parts lists that I use to build these as I build them, and probably in a Google document or a drive for the STLs. But this is the first stream I've done in a very long time, so I'll get all that stuff sorted later, and probably when I edit this, put this on YouTube. So yeah, let's get started. So I'm just gonna put him over here. I'm gonna switch to my overhead. Well, no, I'm just gonna. Okay, so the first thing, I'm gonna lay out the materials that we need to build our guy here. So let me find. Okay, so there's the batteries. You've got boost controllers, servo, a microcontroller, wiring kit. These are great. You can use any wire you like on these. This is specialty, kind of like special low gauge, very, very thin wire. What makes this stuff great is that you can see how flexible it is. How it's just it's almost like string. This is like silicone insulated wire, very flexible. This is great because if you watch the robot in motion, or if you look at it carefully, I know it's the wires are painted silver in the back here, so they're not exactly the easiest to see. But these pieces right here that go from the base, the hips that don't move to the head that does move, you can see how they flex. And again, my camera's not that great, but you can see how the wires flex. And this wire is great because it has it's very flexible. And that means that there's much less resistance. The servo turning the torso doesn't have to work quite as hard to turn and so you can add more wires going from the base of the hip. Let me see if I can get a close up here so you can see what I'm talking about. It's all painted black. It's not great. So you got the wires connected to the base that run all the way down the leg into the base. Those go up to the torso. You can see when I twist these, they flex. If you've got nice flexible thin wire, you can have more wires going to the torso. What that allows you to do is have more LEDs. You can add more motors. You can do all sorts of stuff. The model that we're going to be building today, or not today, but in the next few videos, is probably going to have somewhere in the area of 4 to 5 wires. One of them is going to have fewer because the wires won't be flexing into the head. They'll just be running directly to the motor in the hips. The one with the motor in the head will have to have a few more wires, but that's not a big deal because we've got this nice flexible silicone insulated wire. And I will be, again, linking all the parts I used later on when I edit this. So, and if anyone wants to DM me with questions or parts list, I'd be happy to help. So, let's look at the parts that we're going to use to build this guy. All right. So we've got a few parts here. Today we're just going to, like I said, today we're just going to be working on the base. So we've got the base. I'm going to put my other 90 millimeter. Hold on one sec. So we've got the base. This is the base of an Armiger. I believe these are 100 millimeter, just standard GW plastic that you get in the model kit. Now, obviously, we've got too much equipment or too much electronics to fit, in these little. You've got a few millimeters of clearance under the base. Obviously, that's a bit too much because the battery is just too big. Now, you can use a smaller battery for these, or you can surface mount the battery on top if you want, but you're still going to have to deal with all the boost converter board and the microcontroller. And these boost controller boards can get hot. So you want to give them a little bit of clearance above and below for whatever you're doing. So to solve that problem, I 3D printed this. Now I'm using a resin 3D printer. I'm using an Elgu Saturn. That's a pretty nice resin printer that you can get. I mean, it's a good quality printer. It's pretty, it's like, I think you can get them for $600. This is using standard water rinse resin. It produces a very nice, rigid, thick plastic that you can, it's just a very nice output. This is where we're going to house all of the electronics. You can see in this finished model that we've got the base, and you can see all the wires and the switches coming out of the base. And inside the base, this is going to be very difficult to see because it's just a bit of a rat's nest in there right now. Let me see if I can turn this around. All right, so you can see I've got the battery, and then I've got the voltage converter here, and then I've got the microcontroller, which is like this piece right here. It's again not a great angle. There you go. You can see it a little bit better. It's the microcontroller here. You've got all the PWM wires soldered in here, and the power connectors here. Again, this is my first revision of this, so we're going to do it a little bit better when we build it here. shorten the wires, use more flexible wiring, just stuff like that. So it's a little bit cleaner. The other thing you've got here is the Wi-Fi antenna. These microcontrollers that I'm using, which I'll get into more detail in a few minutes here, they have Wi-Fi capability, and that's really great because with a robot this small, you don't want to have to put a control panel on it. So the eventual goal with these guys is to build a whole army of them and then write code for this microcontroller that will allow us to control the entire army by Wi-Fi. So I can have an app on a tablet that I say, robots dance, and then they dance, and I don't have to individually tell each robot to dance by pressing a button on the base or whatever. And it's also useful. You're going to want to be able to tell the robot to stop, to stay still, because trying to play a game of these are meant to be played in the tabletop, and trying to play a tabletop game with a robot thrashing around and dancing in the middle of a firefight is not good because it's going to knock over terrain, and it's just not great. So you want a way to tell them to stop. Right now, that's going to be the power switch on the back here. You can see I've got a power switch. You can see I've got a power switch here. This just controls. This turns the voltage booster on and off, which tells the entire thing to start and stop. And then I've got this over here, which is just a USB. I think this is micro USB female surface mount, and you can see I've got two wires, just positive and negative. This is for recharging the battery inside. This one you can't use. If you plug this in, it's just going to supply power to the voltage converter. It's not going to allow you to actually program the thing. Maybe I should do something like that. Have this be able to talk to the microcontroller. But for now, these are just used for charging, so you don't have to open up the base. All right, so let's go over each part that we're going to use here. The first part is the battery. As you can see, this is just a lithium polymer hobbyist battery. This is a lithium polymer batteries, very similar to lithium ion, but the packaging and the voltage is just different. It's just a slightly different chemistry. These batteries, this one, you can I don't know if you can see how well you can see it with this camera, but this one is a 2500 milliamp hour battery. Like most small hobbyist LiPo cells, it produces 3.7 volts. 3.7 volts is useful, but it is not what we need in order to run servos. This is a servo. This is what provides all the motion. It's just a little tiny electric motor with some very small circuitry and some gears. These need 5 volts to run. LEDs that we use require between 3 and 3.3 volts to run. This one provides 3.7. So it's a little bit hot for running LEDs. You may be able to run an LED directly with one of these. You're going to want to throw a resistor in there just so you don't burn your LED, but probably not the best idea. So what we need in order to build this for a robot is we need 5 volts, which we need to run the microcontroller and to run the servos. And then we also need 3.3 volts, which is our logic level, to run the LEDs. And also, 3.3 is a very useful voltage for running other peripherals, like if you wanted to add sensors to this thing, or to, there's anything in the Raspberry Pi ecosystem or the Arduino ecosystem, any sensor you connect to those will probably be running either 3.3 or 5 volts. So we're going to want both of those voltages. And by default, this battery only provides 3.7. So in order to get those voltages, we're going to use one of these. Now I'm going to put this under the microscope so we can see it close up. And I apologize for the glare. It's not always the clearest thing. Okay, so I'll try to tilt this up so you can kind of see it. This guy is, you can see it up at the top, an Adafruit Power Boost 1000C. This is a really cool chip, or a really cool board. And I know I apologize again, my lighting situation here isn't great, but yeah, If you go to the Adafruit site and look up Power Boost 1000, you can see all the pinouts, how to use it, what all these little connectors do. Very, very useful site and very, very helpful in getting everything running. So, what does this actually do? So, you've got a number of connectors on here. You've got a micro USB on one side. You've got a battery connector that connects up to this little, you can see the little connector here for the battery. That connects directly to that little black port here. And that powers, that provides output power to the board. So what is the USB for if you've already got a battery? The USB is for providing voltage to charge the battery. So the way this works is when you when you connect the battery, which I'm not going to do right now because I don't want to have it just idling. When you connect the battery, this outputs 5 volts on this side. You've got a number of terminals out here. These pins output 5 volts. So this effectively steps up. It says, okay, we're taking the 3.7 volts. We're doing a bit of conversion on here, and on the outside, on the output, it comes out at 5 volts. That gets us the voltage we need, that 5 volts that we need. So what happens if you run this while you've got, what happens if you plug a USB in here? It does a couple of things. It takes the power from the USB and just runs it directly out, because USB is already at 5 volts. So it takes the power from the USB and you get it directly out this side. But it's also doing something else. It's converting the USB 5 volts back into 3.7 and charging your battery. So these boards do a lot of like really helpful things that you might normally need several boards for. You don't want, normally you would need a charger board and then you need a power conversion board. These guys do both of those at once. The things to note here are that these are power conversion chips. The ICs here can get very, very hot. Hot enough to burn you to the touch. Like, you know, maybe you're not going to like burn your fingers, but it's going to be, you know, you don't want to touch that. This is completely normal and to be expected. You'll see in my design for the base, I've got these two pieces here. These are like these rise like 3 millimeters off the base. This is what we're going to be attaching the power conversion circuitry to, the power board to, just to give it a little bit of breathing room so it can dissipate some of that heat without dumping it directly into the plastic. So just to recap, the USB charges the entire thing. So when this is plugged in, and again, you saw earlier that I showed you the surface mounted USB on the robot. That's connected to this right here. So that I can recharge the battery without having to open the whole casing and, you know, connecting a USB directly to the board. The LiPo cell connects here, and the 5 volt power comes out here. If you have the USB and the LiPo connected at the same time, the USB charges the LiPo. If you disconnect, and it outputs power over here at the same time. If you disconnect the USB, the LiPo cell takes over and powers the 5 volts. So you can use this in effect as a UPS if you wanted to. So you could have, you know, your power supplied by USB and just have the battery waiting. And if the power on the USB cuts out, the battery kicks on and just starts outputting the same power out the other side without any interruption at all. It's great. So that's how we're going to power this guy. This provides the 5 volts. So what are we doing with that 5 volts? Well, I'll show you. This is another Adafruit product. This is a Cutie Pie ESP32 S2. I believe I've gotten that right. Basically what this is a very, very small, you can see the processor on the back here. Very, very small. It's less than the size of a US quarter. You can see how big it is compared to my fingers. This is a self-contained computer. It runs, I believe, I can't remember the CPU frequency on the top of my head, but I believe it's somewhere between 140 and 160 megahertz. It's one core. It has 4 megabytes of RAM. No, I'm sorry, 2 megabytes of RAM and 4 megabytes of storage. And you can get these guys in different configurations with different chips. Some of them have, you can get one with 2 cores and different amounts of RAM, but these are cheap. And you can see this little round thing here this little round connector that connects to a Wi-Fi antenna. This thing has Wi-Fi and Bluetooth, so you can use this to control anything you build over Wi-Fi. It's a bit more complicated than your first Python program, but not by much. So, how are we going to use this? That's the $1,000,000 question. So, the way this works is that we're going to build our power circuit, and what we're going to do is we're going to connect these output pins for power to these input pins on the bottom of here that take 5 volts. What I'm also going to do, that's one way of doing it. You could solder these pins wire directly to these so that it's soldered together, but there's better ways to do it. I like having, just finding all my USB connectors here. I like being able to replace parts to make it modular. So I've got these. You can't see that. This is a surface mount USB connector. So we're going to be wiring that into the mix. So this is going to connect like this. These pins are going to go to here, and then this piece, once it's all wired up, connects directly to this. It's a bit tight, but in it goes. So that'll be connected like that. So it'll really just be this piece connected to this right here, and that will power the microcontroller, and then you're in business. And then we're going to have a simple switch to turn it on and off, which will turn this board on and off. And then we're going to have that USB surface mount, which, let me find one so I can put it on the microscope for you. I really should have done this before, but I'm not very organized. Okay. So this is the surface mount piece that we're going to use on top. Again, very simple. This just connects into USB and breaks out. It's a USB micro female connector, and it breaks out all the pins. You've got power on this side and ground on this side. For a switch, we're just going to use a very, very simple, very inexpensive switch. All of these pieces you can find on eBay, Amazon, Alibaba, whatever. It's all there. You can just order these things in bulk if you want. Usually these are pretty inexpensive. You can get batches of these for like, a batch of 10 for like $10 or something. They're less than $1 each. Same goes for the surface mount micro USBs. These are readily available if you've got like a professional electronics supply store locally. You can get them from there. Shout out to Arcade Electronics in Arlington, Virginia. That's where I go to get a lot of this stuff. Obviously, the microcontrollers and the hobbyist parts you'll need to order from either Amazon or a site like Adafruit, which I would highly recommend. Adafruit. But yeah, so the question, before we get started, I'm gonna show you one that I've already built, what this actually looks like. So I'm gonna scoop all this stuff off, and I'm gonna put this here. Okay, so with mine, I've got a male micro USB connector that I've also added so that we can disconnect that from the circuit if we want to, without having to desolder the entire thing. These pieces are a bit stiff, so bear with me. Then we've got a switch wired into the enable pin, and this board looks different from the other power converter, but it's the same piece. It's just a different color. We've got a switch wired in here, which you can see over here. When that switch is on, it enables the board and power will flow, and it will charge the battery will charge no matter what, but it will actually, that's what when you're flipping the switch, you're enabling the output power that comes through these wires here. Finally, we have our USB-C male connector, which will then connect to the microcontroller like so. These just connect like that. And I need to work on the zoom level of my microscope. It's very, very zoomed in. But yeah, as you can see, to do this project, you do have to do some soldering. Uh, there may be ways to do something like this without soldering, but honestly, if you want to do anything real with robotics, you need to learn to solder. It's just a as much as that sucks, it's just a fact of life. Uh, Soldering isn't that bad. Uh, you just need to do some practice. Um, I would recommend getting if you're gonna give these a try. You can do it with a handheld, with like a little direct plug-in cheapo $30 soldering iron if you want. But I would strongly recommend something like this. I'm going to move my hand cam and show you my setup here. Uh, I've got a Weller soldering station here. This is digital soldering station, so you can turn it on and you can set the temperature that it runs at. I have mine running pretty hot, like at 700 degrees. And then it's got a soldering station here that it will safely hold your soldering iron so you don't burn yourself, which, trust me, I've picked up a soldering iron right on the tip with my hands that I didn't know was on. Those burns take time to heal, and it sucks because they hurt the entire time. Don't do that. Don't burn yourself with your soldering iron. Shit sucks. Um, you can get one of these probably for maybe a couple $100s. I do a lot of soldering, so I use a bit more of a setup than normal. Then you really need to do this. Uh, and then the secret weapon for doing soldering is this stuff. This is flux. I'll show you how this works once I start soldering, but basically it makes the solder run like water and flow right into your solder joints and make everything nice and neat. It simplifies soldering greatly. I've also got some bench equipment over here. Not really going to use it here for this. I may use the oscilloscope to show you some waveforms once we start actually running the microcontroller. When we start discussing PWM, which means pulse width modulation. That's what we use to control the servos. Again, you don't need any of this stuff. This is expensive. I use it. I have it because I like doing electronic stuff, and it really does help. But for this project, we don't need any of it. Ignore it. So, yeah, looks like we've actually got a viewer. So, in case you're interested in what we're building here, we have this. This guy, just to recap real quick, we're building like this, and it's basically a robot. Um, you're taking a GW model for the Armiger. There's some custom 3D printed bits on it to allow for the servos to fit comfortably inside the torso. And you've got some lasers on him as well. You can see the lasers in this shot a little bit. A little quick note about lasers. These things will burn your eyes. Do not fuck around with lasers unless you've got laser eye protection. Trust me, it's real. Don't fuck around with lasers without goggles. The goggles, they do everything. Okay. Um, so yeah, the servos. These are just. I'm just gonna put this guy away here so he doesn't thrash around and burn my eyes. The servos are the next step. I've already discussed the microcontroller, the power converter, and the battery. These are servos. Uh, they look like they've got a little. They look like motors, right? They've got. Let me put these on the microscope so you can see them well. So this is a SG51R micro servo. This is probably one of the smallest, easily sourced servos that you can get. These, like I said, they run off of 5 volts. And these connect pretty much straight to your microcontroller very easily. You can see that these have 3 wires. They have the brown wire is ground. Sometimes it'll be black. The red wire is your voltage, which is going to be 5 volts. And then the yellow wire is your control wire, which is for PWM. And we'll get into that later. It's basically, think about the yellow wire as the control wire. Oh yeah, the bench microscope it's really, I wasn't expecting it to work this well, but this is a just a $50 bench microscope. I think the company that makes it is called Pluggable. You bought it. I bought it off of Amazon. I think it costs like $40, $50. It's just a fixed 10x magnification uh, USB microscope. It acts just like a webcam. No special software needed. I mean, it's good. My only concern is that my only complaint is that this it only has it magnifies about a 3 by 3 inch spot, which is fine, but it doesn't really have. You can focus it, but you can't adjust the zoom. But for $40, not complaining. Anyway, servos. So what this does is it's not just a motor. It has a motor in it, but these are special. Normal motors, if you supply when you supply 5 volts or 9 volts or whatever the motor is rated for, it will spin. It'll spin in one direction or another direction, but it's not controllable. You can kind of adjust the speed by changing the voltage, but it's always just going to spin. Servos, on the other hand, you can control the position. So what this servo does is you can see the shaft on top. This, when you turn this on and supply it with a PWM signal, it has a range of motion of 180 degrees. So when you set the PWM to be 100% on, it goes to 180 degrees. When you set it to 100%, when you set the PWM to be off, it goes all the way to 0 degrees. And you can set the PWM to be, you can tell it what degree to turn to, and it'll snap right to that degree. So as you can see, when I was demonstrating the robot earlier, the robot would swing back and forth, and its arms would go up and down. I'm doing that by specifying. I'm telling the PWM to count from 0 to 180 to swing back and forth, and it's a bit more complicated than that, but we'll get into that in another video, probably the next time I do one of these. But for now, just know that this is kind of how servos work, and there's plenty of great YouTube videos out there that show in detail how these work with the gearing, the circuitry. If you're interested, I'd highly recommend it. Definitely looking into these. These are, just the knowledge of how these parts works is critical in actually building these things. But the important thing is you've got the 3 wires, you've got the plug on the end. You can get setups for learning how to use these that you can plug these directly in without soldering. But for this project, because of how small everything has to be and how compact the wiring has to be, we're not going to be using the pluggable. We're going to snip this off, and we're going to solder it directly to the microcontroller. All right, so this works at 5. These work at 5 volts, but we also need 3.3 volts for the LEDs that I'm using. Now, I said I was going to show you all how to do LEDs, and I will, but let me show you the LEDs first. This is a super tiny LED. I believe this one is green. These guys run at 3 volts or 3.3 volts too. They're super bright. You saw the one in the robot I had earlier in the eye, and these are great because they're very durable. These tips are very strong because it's like a glob of resin that the LED is encased in, so it's very strong. You can see here that you've got 2 wires. One of them is silver. That is the negative lead, and then the other one is copper. That is the positive lead. These take 3 or 3.3 volts of power. So how do we get 3.3 volts of power if our booster board only provides 5 out of these pins here? That's where the microcontroller comes into play. The microcontroller takes 5 volts in its USB, and there's a voltage regulator chip on here. You can see it. I'm kind of pointing to it. It's a little black looking thing with the 5 legs coming out of it. What that does is it takes 5 volts and it steps it down to 3.3, which is the logic level that these boards use. The processor, which is on the bottom here, uses 3.3 volts. It also, because these boards are meant to be used for projects like this, I'm going to use my little screwdriver as a pointer here. you've got 3 pins here. You've got 3 volts, 3V, which is actually 3.3 volts output. You've got ground, and then you've got 5 volts. In order to make a circuit to like light an LED or to run something else, you would connect the positive lead to 3.3 volts and the negative lead to ground. Ground is like, if you're thinking about electricity like water running through pipes, this is 3.3 volts would be your water supply, and the ground would be your drain. So the voltage, to simplify things, it's not how this really works, but for what we're doing, this is how we can explain it. The water flows from here to here. Now, think of 3 volts as a nice, trickle of water, with 5 volts being a little bit more water. Like, if you turn your faucet to half, that might be what three volts is. If you're running your faucet full blast, that's what 5 volts is. So we want to make sure that we're running the right voltage to the right sources. Motors need the 5 volts. LEDs need 3 volts. So we're going to be running wires from here, here, and here. And also, our PWM, which is going to be our control wire, are going to come out of our AW, A1, A2, and A3 wires. For this project, we're just going to use maybe 1 or 2 of these. One for the motor, one for the LEDs. Yeah, that's the more you learn about the way electricity works, the more complicated it gets. There's like layers of understanding here. You can go, the layer that I'm talking about is very elementary, because we're using hobbyist stuff that already sets the voltages and kind of does a lot of the work for you. We could speak about it in a very simplified way. 3 volts, 5 volts, job done, easy. But when you're building things like some of these robots like that I've built, like if I was to open this one up, which I can't because it's glued, but inside the head here, I've got, because this has lasers, I need to be able to control the lasers using PWM, but I need to do it with a higher voltage, with a higher amperage than the PWM allows for, because the PWM supplied by these microcontrollers is like 20 milliamps, whereas the lasers need 40 milliamps. These are pretty small 3-volt lasers to run, but I still want to be able to control them, so I don't want them to be on all the time. So I'm not hardwiring these to 3 volts. So inside I've got a voltage regulator, I've got a transistor, and some resistors that allow me to boost the PWM amperage through the transistor into the lasers, so that I can control these things with software. But that's outside of the scope of what we're doing here. I don't want to scare anyone off, because transistors are a little bit complicated when you're just dipping your toes in. So the ones we're building here, very simple. We don't have to worry about resistors too much, or transistors at all, because we live in a great age where we have all this hobbyist electronics where everything's documented. It's very easy to use. If you can pick up a Raspberry Pi, you can get started easy. So let's look at how we're going to put this together. So we've got our base, right? You can see the 2 parts here, where these are the risers where the power converter is going to sit, because like I explained, it gets pretty hot. And connected to that, we're going to have a switch, and then we're going to have the battery down here. And yeah, let's get going. All right, so and like I said, I've already got this power circuit built. I'm going to show you how it orients within, but we're going to build one from scratch here. So yeah, let me just plug this stuff together. All right, so we're going to build this circuit here in just a few minutes, but I want to show you how it fits within. So let's switch to bench. So basically, we're going to put the voltage converter on its little stand here, and we're going to hot glue this in place. Hot glue is great because it's semi-permanent. You can glue it on here, and if you really need to pull it off, you can just kind of put a screwdriver under there and pry it open, because it's not like super glue. It doesn't lock it into place forever. Voltage converters going there, the chart, and also the charge circuit. And then we kind of put our battery here. You can just take the wire from the battery and connect it to this little plug like so. From there, we'll take this surface mount micro USB. We'll drill a hole in the 100 millimeter base for this and the switch, which you can see right here. This just switches on and off. I'm trying to. It just switches on and off, and then we're gonna mount those both on top of here. So we'll Dremel or cut a hole for the switch and the micro USB thing here, and that'll be just on top. You can see that how I've got that done on this one here. So we've got a switch and the micro USB, and they're just kind of, these are, it's hot glued and super glued onto this. Well, you can do it more elegantly by putting screws in these holes, or by screwing the switch in. It's also got holes. But there's some of these things are, you just got to do what works. So another thing I want to show you is that there's a hole in the bottom of this. There's two reasons for that. One, when you're printing this, especially with resin is a fluid, and you can see the support marks here. You want it, when you're printing these things, you want to have a place for the resin to drain. So we've got this hole, because otherwise, if this was solid, you'd get resin pooling in here and it would be a goopy mess to clean. The other thing this does is it kind of allows a little bit of airflow. There's not great airflow here. It's not needed, but just a little. It's not sealed. We want to make sure that air can move in and out of this, especially if you're gluing the base to the top of this rather than magnetizing it like I do. But okay, let's get started actually building this thing. All right, let me heat up my soldering iron, and all right, I'm gonna have to switch back and forth between the overhead cam and the soldering iron at the microscope quite a bit here, so try to keep up. So the first thing we're gonna do here is wire up the switch. Now, let me tilt this up so you can see the markings here on the pins. Okay, so you can see here, where's my screwdriver? We have an EN pin and the ground pin. So basically what the enable pin does, which is the EN, is when it's switched to ground, when the switch is connected and the switch is on, it takes enable and it dumps it directly into ground. That tells this chip here, the voltage converter, no output, switch output off. So when enable is connected to ground through the switch, the whole thing switches off. You'll still be able to, if USB is connected, you'll still be able to charge your LiPo cell through the connector, but it won't output anything here. That means we want that because we want it to be able to turn it off with a switch. When the switch is disconnected, meaning the switch is off, this is active. So if there's a battery or USB, it will output. On and off for these switches is just one position or the other. Like, these are very simple switches. You just on, off, whatever. So you'll be able to tell when it's on because there's a little battery, there's a little light that'll light up here. So let's go ahead and set up our switch and get that soldered in. All right, so I've got my solder. This is just pretty conventional rosin core solder. You can get this off of Amazon or some hardware stores, pretty cheap. I would recommend against using lead-based solder, simply because lead's nasty. You don't want it in your environment. You don't want it in you. Yeah, so if you use this stuff, this is lead-free. It's got a flux core. We're going to be using some additional flux just to help the solder run. And before I do this, very important, I'm going to set up a fan in my window just so I can blow the fumes out, because I don't want to be breathing this, even if it's lead free. You know, exposing yourself to chemicals is an occupational hazard if you're doing a lot of soldering, but there are some steps you can take to protect yourself. I'm just putting a fan in my window, so if you hear birds chirping out there, that's what's going on. And I have to blow the exhaust out the window, just to keep airflow here. All right, so my soldering iron is warmed up, and the first thing I'm going to do is cut some wires here. Now I'm going to solder the wires onto the board, but I'm not going to solder them to the switch. I'll show you how they're connected to the switch, but I don't want to put them on the switch yet because we're going to need to snake these wires through a hole in the base, and it's harder to do that when they've got a big switch connected to them. So I'm going to I'll solder the wires to the power converter and leave these exposed so that I can snake them through, and then I'll show you how later on how to wire up the switch. It's very, very easy. So I'm going to trim these to about 5 inches or so. You know, that's plenty of space, and this is just a cable snip, a wire snip. 5 inches is good. You want to trim. You want to kind of leave your wires long when you're trimming them, just so it gives you some slack. We won't be using 5 inches of wires for the switch, but you know it just gives us some breathing room. So I'm going to snip these. I like using standard red and black. Actually, I might use different colors here because these aren't really carrying power. Red and black, generally, anything, you know, a colored wire and a black wire are usually used for denoting these wires. You know, the black wire is ground, the colored wire carries power. I'm going to set these aside because I'll use these later. Just so we know that these are not carrying power, they're just carrying signal, I'm going to use these yellow and green wires. And when I say it's just carrying signal, the amount of power coming out of the enable pin here and going to ground is very, very small. It's just a signal. So these wires aren't really considered to be carrying power, so to speak. You couldn't power LEDs or anything off there. You wouldn't want to, not out of the enable pin. That's just a signal to the board to start up or shut down. So, okay. So in order to do soldering, first you've got to strip the ends off of your wires. I like giving them a couple of millimeters, just nice and clean. Put that on the microscope so you can see what I'm talking about. Yeah, like so. Very clean, just a couple of millimeters to poke through the solder hole, or to poke through the via on the board. Oh yeah, the tool that you're gonna want to pick up in order to do any sort of wire, stripping of wires is one of these. This is just a wire stripper. It's got some adjustments for multiple gauges, but basically what this does, it takes the insulation, which is the plastic surrounding the wire, and it snips it while leaving the wire intact. So you can get these at any electronic supply store. They're very cheap, probably $5, whatever. I've seen people strip wires by biting them. You can do that, or you can do it with like an X-Acto knife, but you're eventually going to mess up your teeth, and you're going to cut yourself. These are easier. They make it trivial. Get yourself some proper equipment. Don't fuck up your teeth, or cut your hand open. There'll be plenty of time for that later. All of these projects that I'm building, the robots back here, they have my own blood in them as an ingredient. So, okay. First thing we're going to do. Oh yeah, your teeth. We're going to solder a wire to the enable pin, the EN, and the GND vias here. That's very, very simple to do. I'm going to try and do it on my microscope. Might be a bit easier said than done. All right, so I'm going to go ahead and do this. I'm going to try to keep it in frame while I'm doing it. Basically, I'm going to take these and put them through the back of the board, so that, and then I'm going to fold the wire over. So you can see kind of that I've got a wire, and this can be very fiddly to do. I might need to snip a little bit of slack off on this wire to make the lead a little bit longer. All right, so I've snipped the wire. I've stripped the wire a little bit more, and I'm going to twist the fibers so that it's nice and stiff. And it's just one wire. I'm going to stick it through the enable pin here. I'm going to fold the wire over so it stays put. So you can see that I've got a nice connection there. I know a lot of people watching this who don't like soldering or don't want to learn how to solder are going to say, "Oh, that looks solid." It's not. It comes easy. It comes off easy. It's not going to be stable. It's just good enough to hold in place while we're setting our wires up. So you're going to need to solder this. Soldering is not hard. It's a bit intimidating to get started with, but it's a valuable skill to have. So learn it. All right, so I got my other wire retrimmed so it's a little bit longer. And I'm going to put this one through the GND hole, which is the ground hole. I'm just going to pinch this one over. So as you can see, I've got the two wires in the holes that we want them to, enable and ground. So my soldering iron is over here. It's all heated up. So what I'm going to do to make these solder joints nice and clean is I've got my flux. This comes in a big syringe with a pin on the end of it. Don't inject this shit. It'll fuck you up. All right, so you can see on the microscope, I'm going to take a nice little drip and put it on each terminal. So what flux is it's kind of this greasy, waxy crap. It's really awful stuff, but it does something very, very important. Solder, when you use it, you put a little bead on the end of your soldering iron, and it looks all silver and nice, and then you try touching it to anything, and it just doesn't want to stick. You try touching solder to any metal, it's just it's gonna be obnoxious and it won't stick. You want it to stick and you want it to flow into whatever you're soldering on. The reason why solder does not stick usually is because it oxidizes very, very quickly, which means it forms a layer that reacts with oxygen that makes it's almost like it's surface tension with water. It doesn't want to stick to anything. What flux does is when it heats up, it breaks that oxidized layer. So it makes your solder just flow and make those nice little beads. It's very, very helpful. So here's how we do it. You've got my soldering iron here. This is the tip. Just the tip. You can see it's nice and clean. I've scraped it down. So I'm going to take a little bit of solder, and you can see I've got my bead of solder on here. You don't need much. So what I'm going to do is I'm going to take that solder, the bead, and just press it onto each one of these joints. And just give it a little heat on the board to make sure the solder goes in there. So I'm going to so each of these needs its own little drip of solder. And just be very careful not to bridge the two pins together. And yeah. You'll know you've got a good connection when the solder is fully, you can see here kind of that the solder is fully down into the via. The via is being these little holes. Once you've got the solder all the way down in there, it'll just, if you're using flux, it'll just flow in there like water. And yeah, you're good to go. I'm going to put a little bit on the back here just to make sure we've got a good connection and to make sure it's stable. Probably don't technically need to add flux here, but I'm going to do it anyway just because I want to make sure it's in there. And yeah, again, flux is going to get everywhere. It's going to get in your hands. It's going to get in your hair. It's going to get in your, try to keep it out of your mouth. It's not supposed to be toxic, but whatever. All right. So I'm going to do the same thing in the back here. If you think you've got a good connection, you don't really need to do this, but I like having nice, neat solder joints on both sides because it just adds strength. All right, cool. All right, so yeah, those look good. You can see I'm not the best soldering. I'm not the best at soldering. Let me get a paper towel and wipe the flux off. But you can see that these are in there pretty good. And on both sides, they're secure. Again, you kind of want to use a Q-tip with some isopropyl to wipe your flux down. You don't have to, but this stuff can be corrosive. So it's good to have. Yeah, you can see that there's no bridging between the pins. It's pretty difficult to bridge pins when you're using flux because the flux wants to go into the little holes rather than across the gap. And you can see that the wires here are the green wire's got a little bit of the wire itself it's a bit too long on the underside, but that's fine. It's not going to cause any problems. So yeah, what we'll do eventually is connect these wires to that switch. So that's the on-off switch wiring. The next things we're going to want to do are to set up. Let me find the pieces we need to do this. The output. So you can see here that one of these is marked plus and the other one is marked minus. We're going to want to line that up here on this. You can see that one of these pins, there's 4 pins on this. This is a male USB-C connector that you can use to break out the pins. It's got all the pins for data on the back here, but we're not actually using any data. This is just for power. So we only need to use 2 solder points here. You've got the G and the V. The V is for volt. The connects to the positive lead here, and the G connects to the negative lead. Just ignore the plus and the minus here. That's for the data pins. So this is what's going to connect to our microcontroller. The power comes out of here, it goes into here, and then this connects to the microcontroller. So again, we're going to do the same thing. We're going to use those red and black wires that I cut earlier. I'm going to trim the ends, and then I'm going to solder them in. I think a better wire cutter. That one's a bit dull. So again, trim the ends, both ends this time, because we're going to go ahead and solder this in on both ends. And then I'll do the soldering. Okay, so again, we want to keep we want to use either a red or a colored wire to connect to the positive lead here, and we want to use a black or a dark colored wire to connect to the negative and ground lead, just so we know which polarity our power has, just to keep things consistent. So I'm going to just verify my work on this known good one here to make sure I'm wiring these up properly. Yeah, okay. So let me get that on the microscope. Okay, so that's the V. Yeah, okay. Always double check what you're soldering before you solder. It's like carpentry. Measure twice, cut once. Here we're verifying twice, soldering once. We want to make sure. I mean, you can desolder things, but it gets really messy, and it's never going to be quite as good as a fresh, done right the first time soldering connection. So yeah, I'm just looking at a known good example that I've already made to verify that I know what I'm doing. Okay, so we're going to connect this red wire to this. You can see the plus sign up here. and then this row of 4, this is for connecting a USB terminal. If you want to do that, you can connect a full-sized USB connector. Let me see if I've got one of them here. There, if you want to. We're not going to do that because we're not using this to power USB. So what we're going to do instead is use these terminals here. This is the plus, this is the minus. So I'm going to go ahead and solder my red wire into the positive terminal here. Come on now. Getting these clipped in here is a little bit obnoxious sometimes. I have to give myself a bit more. And you can see the flux on my microscope board just as a demonstration of how it gets everywhere. Because when it heats up, it gets very fluid. All right. So I want the red wire into the positive lead hole here. Just going to pinch it down so it's nice and secure while I solder it. And then I want the black wire through the negative lead hole. All right. Okay, so you can see, you do the same method to get your wires through. You pinch the excess over, just like you're doing it in the first step. I'm going to give myself a little bit, try to do a little bit less flux here, but we'll see what we can do. You can make a mess with this stuff if you use too much. Tell my soldering iron to stop going into standby. I needed to heat back up to full temperature. I caught it right as it was trying to chill out, so I don't want it to do that. I'm gonna add a bead of solder to my iron. See that there? And I'm just gonna press it and hold it just for a second. You don't want to hold these. You don't want to hold the soldering iron to your board for too long because you can damage the surface of the board. 1 to 2 seconds is usually enough to heat things up. Make sure the solder's flowed all the way in. And now the negative lead, do the same thing. Okay, it's being a bit of a butt here. There we go. And in between soldering beads, I'm just wiping all the excess solder off on a wet sponge on my. Here, let me show you. On my soldering station, I've got a nice wet sponge here. Just cleaning all that crap off there because you get burnt flux, you get all sorts of junk, oxidation on the end of your soldering tip that makes it difficult to get a soldering bead sometimes. So you want to keep it clean. But yeah, you can see that these solder joints are nice and shiny. They go all the way through. Pretty clean, right? So I'm gonna kind of try to trim the leads off the wires that are sticking up through, because once they're soldered, you don't need any extra stuff sticking out. And if you have too much stuff sticking out, too much extra wire, it's just going to cause you increase the chance of having extra contact that you don't want going on. So I'm just going to take that little extra bit of wire off so it's nice and clean on the yeah. All right, so we've got that soldering done. Now we're going to do it to the surface mount USB piece. So again, verify what you're doing. I'm going to trim this down a little bit because I don't need quite as much slack on this end. Verify what you're soldering. Make sure you know what the wires are doing. Otherwise, you can damage your electronics. If you reverse the polarity, like if you put voltage into ground or ground into voltage by accident, you short circuit, it won't work. Then you spend hours trying to figure out why, because you crossed a couple of wires. Ask me how I know this. I could probably count the amount of time I've spent trying to figure out why something isn't working in the hundreds of hours. And that's conservative. And I don't do this for a living. So I'm sure the master electrodes out there know that pain. All right, so I'm gonna take these wires. I'm gonna kind of add a little bit of electric tape here to tape them down because I don't have a third hand. Um, so I'm gonna tape these down so I can have them nice and secure. I'm gonna angle these up a little bit. All right, so the first one I'm gonna do is my positive lead. Get the negative one out here so it doesn't get soldered by accident. You can see, kind of see how that lead is just resting on the pad. I kind of align it a little bit better to make sure it's got a good contact. I'm going to put a drip of flux here. Make sure everything's nice and fluxed up. That should be good. It looks wet. Cool. All right. Again, little bead, doesn't take much. I'm going to try and do this without dislodging the wire. So yeah, because I'm using flux, the two pieces of the metal from the wire and the metal from the pad just stick together with the solder instantly. It's very, very useful stuff to have when you're trying to do anything with soldering. Just try not to burn the wire leading back to my soldering station. Okay, so that's on there. That's pretty solid. So I'm gonna do exactly the same thing with my negative lead. I'm gonna put that on there with a bit of flux, just a smudge. Okay. More solder on the iron. Get that drip in there. I'm going to kind of push it into place to align, and then just take the solder and get it on there. Where's my drip? There it is. Come on. This can be frustrating and fiddly and obnoxious to get these wires to line up, especially if you've got them aligned slightly wrong. All right, that should be good. Let me see if I've still got my solder drip. Yeah, he's there. All right. It's not on there all the way. Not very well. Connection will probably break, so I'm going to push it back into place a little bit better. I'm going to add a little bit more flux because I don't think I had enough on there to begin with. If you're trying to solder a joint together and it's not going, or the solder doesn't want to cooperate, you didn't have enough flux, or it burned off prematurely, or you didn't have enough solder. If it's not cooperating, just back off, try it again. Ah, shit, come on. There we go. Okay, that's finally on there. Sometimes it just does be like that. They don't want to, the little bits don't want to line up. They don't want to solder. Whenever you're done soldering some connections, you want to take a second to just inspect. You want to, again, you want to verify that your work is good before you move on. Otherwise, you're going to stack up your errors, and that is annoying. So we're going to look at this. You can see there's no bridging between the connections. We can verify that the black wire is on ground, the red wire is on voltage. I'm going to wipe some of this flux off here, and you can leave it on there, but it's just a mess, and it will get all over everything. All right, so we verified the black wire is connected to ground on that side, and the black wire is connected to minus on this side. Red wire is connected to plus, and it's connected to the the V on this side. So this connection is solid. If you'd like, you can take more steps. You can get a multimeter and test the continuity between these connections. But for something this simple, and because I've already built this design before, I'm just gonna roll with it. I can test it if I need to, but for the time, I'm just going to let it go. All right, so we've got our power switch wiring and our power wiring. Next step is to do the same thing with the input. Just digging through my box of bits here. Where's my micro USB surface mount? Ah, perfect. Okay, so next up, we're gonna build just a. I'm gonna move our booster circuit out of the way here. So what we're gonna do is we're gonna just make a pair of these. This is a micro USB female surface mount jack, and this is a micro USB male surface mount jack. They fit together here, just pretty much pretty standard USB connectors. What we're going to do is we're going to link these together so this one draws power off of this one. This one's going to go on the surface, and this one's going to go on the inside, and it's going to connect to our charge circuit. So we can have this guy sitting on top, so you can connect a USB cable to it, and it'll charge the whole circuit that's down inside the base. And you can wire this stuff directly to the charge circuit if you want to. But I like being able to have this piece plug into the charge port here, so that I can unplug it if I need to. Like if I want to run an actual USB connection cable here, I can if I want. Or if something breaks, I can replace it without having to desolder a bunch of stuff. So what we're going to do is make this connection right here. And let's see. Let me check to make sure the labeling is correct. As you can see, there is no markings on this piece. You've got to be careful here to make sure you understand where your pins are going, because there's no V or no G on here. What I do when I'm building these together is I connect them before I solder, and you can see the traces. This far pin here goes to ground. This pin here goes to V-bus, which on this connector is our positive lead. So what I'm going to do is I'm just going to wire loops like this. So yeah, let me go ahead and trim myself some wire. I'm going to use red and black again, just to denote that these are power carrying wires. And I'm just going to give myself a few inches. Chop that off and trim the ends. We've all seen this before, so I'll just go ahead and do it quickly without explaining everything. The problem with this wire is that it's so thin that my strippers don't always get a good grip on it. Okay. So what I'm going to do is I'm going to wire this up like so. Actually, that's ground. This red wire should be down here. Always check what you're doing, because if I had left that there and wired it like that, it would have been wrong. And then the black wire goes here. So it's going to be like that. I'm gonna leave this side of it unsoldered because, again, I want to be able to, or actually I'm gonna do it the other way. I'm gonna solder this side and leave the surface mount piece unsoldered, so that way I can snake the wiring up through the base without having to cut a giant hole for this piece here, or for the surface mount piece. So here's what we're gonna do. You can see the ground is on this side, which means that flows directly to this pin here. So I'm going to get this soldered up. Again, I'm going to use my little piece of electric tape to kind of keep these wires under control. this can be a bit tricky getting these to stay the way you want, but something like that, right? Okay, so these are actually backwards because I wasn't paying attention. Anyway, I'm gonna solder the red one first. So I'm just gonna kind of lay it in place. Let me trim this a little bit so we don't have too much wire hanging off the end. All right. All right, so you just want a little bit. So I'm going to lay this directly on the terminal that I want to solder, which is this the far end pin here. I'm going to put some flux on there. Flux can act like a little bit like a glue to keep the wire from moving, but only if there's very small forces there. And then I'm going to get my soldering iron, put a little bit of solder there. Okay. I'm going to try and do this cleanly. This can be a little bit obnoxious. And just when you're holding a soldering iron, be very aware where the tip is. What I'm doing now is dangerous. This, having my, the soldering iron in my offhand while I'm, moving around in close proximity with my other hand. All right, just touch. Come on. All right, so that is on there. That's a clean connection. You got to be careful when you're using connections with like a plastic backing here, because if you put too much heat into it, you can melt the whole thing, and that sucks. You'll ruin your connector, or just make it really ugly. All right, so clean off my solder tip, and then we're going to do this the whole thing again on this side. I'm going to trim this wire a little bit because it's a little bit on the long side. Okay. So you can see, just verify the ground is on this side, which means this pin right here is ground. Some more solder on the iron. All right. So just got to solder this up. Come on. Ah, Jesus. Okay, that looks good. All right, cool. So that is our microcontrollers, or our power converter side USB connection soldered in. I'm going to pull the tape up and make sure everything fits. Okay. So it's always good to inspect your connections to make sure they're solid. They don't need to be, if you really, really pull on these things, they will come loose. So just keep in mind it's delicate, especially when connecting these things together. Be very careful, slow, deliberate. All right, so this is the way this works. We just soldered this on. This is where our power is going to be coming in. That connects here. All right, cool. So looks good. So we've got all of our wires coming in and out of the boost controller, or the power booster. We've got our power to the microcontroller. We've got our wires that are eventually going to lead to our on-off switch. And then we've got our extension wire that will lead out to the surface mount USB for charging. Now, you just want to take some time here to look this over to make sure that you didn't fuck something up, because it's very easy to do. Like, I like consulting a micro USB pin, like all the pinouts, to make sure that we're doing this correctly, to make sure the connectors are oriented properly. So I can see here, I'm Just going to plug this back in just to make sure I'm doing this right. We've got black wire on top matching the ground pinout. This is, ideally you'd want the pinout for this little connector here, but since we don't have that because this is cheap, we're just going to kind of. I've also got I've got a pre-built version of this that I'm going to compare against. So we've got, unfortunately on this version, I'm just using blue wire all around because I kind of know what I'm doing with these. All right, so I'm just going to look at how this is built. We've got the ground wire connected here to the ground terminal on this piece here. The V-bus, which is red, on the other board. Yeah, so that's wired up properly. All right, so now we actually get to start building this thing. So if you recall previous steps, we've already printed out this piece here. And I'll provide the STLs when if you see this on YouTube, the STLs or links to the Google Drive or something will be in the description. Not sure how to do that. I don't really have them shared here yet on Twitch, so look for this on YouTube. I'll probably put some information about how to find it at some point here. Yep. So we're gonna go ahead and put our power booster board on these little risers here. I'm going to heat up my glue gun and we're going to get started doing that. Glue gun. Find a open port on my power bar here. Then let that heat up. Take some time and clean some flux off of my stuff. Make sure there's none sitting around. Again, it won't harm anything if you leave some flux on there. It just tends to get all over the place. And having things be clean is always helpful. All right, so as you can see here, we're going to want to have the battery port on the charge circuit facing downward, so it's you don't have to loop the battery and have it be the wire in the battery and have it be all awkward. So, yeah. Let's see if this glue gun is ready. Almost. It's getting there, I think. Just be careful with glue guns again. You can burn yourself. Let's see, try to get some glue out of here. But basically, this thing is going to sit in this little part right here, like so. Get the bench cam in. I'm going to go ahead and turn off my soldering iron for now because we're not going to need it for a few minutes. You can see I've got this kind of in here like that. It's on the little riser bars here because the part that gets hot is this chip here under the battery connector and sometimes this chip here. So we want to have those, make sure there's some there's some breathing room for those. And using hot glue to do this can get kind of globby, and there'll be little strands everywhere. But just hot glue doesn't. Circuit boards don't care about hot glue, so feel free to just glob it on there as long as it's attached. I'm going to put some hot glue on here, and then I'm going to stick the board down on it. Assuming this thing is actually heated up. There we go. You got to move pretty quick with hot glue. It's not quite as bad as like super glue, but it will solidify on you. So you've got to kind of press the board in there for just a few seconds until it cools down, and then you can kind of just give it a tug to make sure it's on there. We're good. This is good. So yeah, the next step is to take our battery. As you can see here, I'm going to switch to the bench mode. There we go. Take our battery, as you can see right here. Very, very important. Do not solder anywhere on the surface of the battery. Do not use hot glue on the battery. You do not want to puncture, damage, tear anything with the plastic membranes here. This is like Kapton tape and plastic. Tape these down. Do not glue them. I leave them just with a piece of like masking tape, even just over the top, or like a roll of just tape underneath. You do not want to mess these up because these will blow up. That's the downside of lipo batteries, is they're a little bit volatile. Uh, you don't want to charge these unattended. You don't want to, I take the batteries out of my models and put them in like a metal box when they're being stored, just so if they do pop, it's not going to start. It'll smell really bad, but it won't start a fire in your house. Uh, these batteries are relatively safe. I mean, these are sold with warranties, but don't abuse them at all. You gotta use these as a responsible adult. And I am making no warranty that these are safe in any way, that the circuit is safe. It's safe, but make sure you know what you're doing with these. Don't leave these connected for long periods of time when you're going away. You just be safe. They're a little bit more volatile than lithium-ion batteries. Do not fly with these things. Just pay attention to what you're doing. If at any point you see smoke coming out of one of these things, disconnect it, put it in a metal container, take it outside. Just, watch for these things to bulge. If they're bulging, that means the battery's bad. You don't want to use it anymore. But I'm just going to connect this thing up just so we can see, to make sure that it's a good battery. You're going to notice there's a little notch here. Make sure the notch lines up with a notch on the board. Okay, so we've got a blue light here. If you look at it, that is the blue light is labeled power. That means power is coming out of the output here. If I were to take these and connect it to the microcontroller, which I will do just to demonstrate, because this is a USB-C controller, it doesn't matter which side which direction orientation we put it in. You can see microcontroller is happy. It's got a little multicolored light that's pulsing here. That means it's good to go, which means our circuit is thumbs up. All right, so I'm going to disconnect the battery and disconnect the microcontroller. But yeah, you just want to test it incrementally like that. So, all right, so it's off. So this is basically how things are going to be oriented on the inside of here. The next step is to take our leads here and do something with them. These need to be connected to the switch. These are going to be connected to the surface mount. So where did I put my base? Don't burn yourself with your hot glue gun, because these things are just going to continue to be hot over here. I'm going to disconnect this while I'm not using it, so I don't burn myself if I put my arm down on it. All right, so the next step is we're going to have to see how we want this to be oriented. It's going to fit together like this. So the way this is going to work is this wire is inside. It's going to be curled up in here and connected, so we don't need to worry about that. We do need to think about where we want to put our switch and where we want to put our surface mount. So usually I like putting them over. If you orient the base like this, just put it down. I like putting them over right next to the power converter, or on this side, so there's a little bit of space for the switch and the wires to come down. So yeah, just like this. So what I'm going to do is I'm going to go over here and get my little finger hand drill. Assuming I can find it. You see how prepared I am right now? I'm organized. Really? Bear with me here for a second. Okay, so here's another good tool to have. It's just a finger drill. You can replace the bits on it by twisting this. This is just a bit that's a little bit wider than the insulation on the wires. so you can drill a hole, the wires will fit through easily. So I'm going to have to do some cutting on these boards as well, or a cutting on the surface here to fit the to make a square or like a rectangular hole for the switch to fit into the base. This is basically a scalpel. It's an X-Acto knife with a replaceable blade. Be careful with these. These are not toys. This will cut deep into your finger if you mess that up. Just always pay attention. Always keep the lid on it when you're not using it. Just don't be an idiot. All right, so I'm going to start doing this by kind of figuring out where I want the holes for the surface mount. I'm going to lay the surface mount on here to see where I need the holes for it for the wires. So assuming I put it like this, the wires will come out down here. Everything's insulated, so we don't need to worry about the battery. So I'm going to say, okay, I'm just going to score the surface here, drill into it a little bit. I'm not going to drill through it because you do not want to use a drill when you've got a battery underneath your drill bit. I'm going to put the wire, I'm going to score the holes right here. I'm just making little marks here. I don't want to, again, you do not want to ever risk drilling into a battery. This will catch on fire and explode if you drill into it. So I'm actually going to remove this battery from the casing here altogether because I don't want to accidentally do that absent-mindedly. So I made some score marks on here. I'm just going to drill through. These are going to be the holes for the surface mount USB charge port. You know, you can the plastic GW uses for all these components is very soft, so you can just drill right through. So yeah, the wires for that surface mount piece will just go right through those holes. So just kind of, and then we need to put, so the surface mount piece is going to go like that, and you can see the holes. That'll line up quite neatly. So the next step is we're not drilling holes for the switch, but we're cutting a slot. So the switch will have a place to go. This can get obnoxious. The easy way is to use a Dremel. Alternatively, you can cut the slot using this. I'm actually going to use a Dremel because I just want to get it done. And I don't want to cutting through these bases with one of these X-Acto knives is it's difficult. So I'm not going to do it. I'm going to get my Dremel. All right, so quick safety. Use safety glasses when you're using a Dremel. You just need something to protect your eyes. So little bits of flying crap don't get in there because you don't want that. I'm going to use my laser goggles just because I have them close at hand. But these aren't ideal because they block a lot of light, but it's enough that I can see. So yeah, really for the switch, I'll take these off for the time being. The switch is going to go right next to the surface mount. What we want to do is drill a small slot so that this rectangular part can sink into the board. So you've got the edges, the connector points here that will sit flush on top of the board. So I'm just going to drill. I'm going to make it so it sits right, and it insets into the board right next to the surface mount, the USB surface mount. So the way I'm going to do this, I'll put my glasses on first. I've got a cutting disc on this Dremel, and I'm going to just make a small slot here. I'm trying to do this on camera without killing myself. You don't need to press very hard. See, I've made 2 parallel cuts here. Okay, so you don't need to do much dremeling. It just takes a second. Like I said, the plastic is very soft. You don't want to dial your Dremel all the way up to 11. You don't need it. You can do it at a very low speed. The reason I say that is because look at this. Just the heat from the Dremel cutting has melted the plastic. If you dial that up to as high as it'll go, you'll get a lot more melting. It'll be a lot messier. So just take a moment to smooth that out. You can use a sanding block here. I'm just going to scrape it away using my knife, just the debris. You can use the back side of your knife. You don't need to use the cutty side until you've got, you want to do it both sides and not wave a knife around in your face. That's key. So you've got these two pieces. I'm just going to snip out the piece that's in the middle here between the two cuts, and just pull the piece out. Just cut a slot. There's no one way to do this. It's if you want to use a knife, you can use a knife. If you want to drill holes and then cut between them, you can do that as well. And it's clean up the edges so everything's flush and looks nice. I'm using the X-Acto knife just to widen this a little bit. And the end result is that you've got a slot in your base. And the switch should fit in there. I'm gonna, you're gonna have to clean it up a little bit, maybe widen it a little bit. As long as you've got the slot cut, widening it and cleaning it up is really not a problem, because you can just, the plastic is really, really soft. You can just kind of shave with your knife off the sides to make sure you're not cutting into yourself in a way that your knife is going to slip into your hand. And just press that switch in there, and there we go, nice and clean. And you can place the switch anywhere you want. You can cut into the side of this, put it here. There's this is just the way I do it. There's no right or wrong way to do it. So this is the way this is going to sit. If you want to, you can have the switch aligned to the side of it doesn't really matter. It really also depends on what you want to do with basing. Like if you want to put, your armature is going to be standing on the base. If you want to put all sorts of crap on there alongside of it to make it fancy, you're going to want to consider where you're putting your switch and your charge port. You can integrate this stuff into your basing. It's up to you. But anyway, so now that we've got that done, I'm going to start snaking these wires through. So we cut the hole, we drilled the holes earlier for the USB charging port. So I'm just going to snake those wires right up through there. We want to pay attention to the polarity. So we want to run the ground wire up through the hole next to the ground port, and the red and the voltage wire up to the hole. So that way you don't have to cross the wires on top of the base, and it'll just look cleaner. It's not a big deal if you snake the wires up through the wrong holes. You'll just kind of cross them onto the surface mount when you're soldering. All right. So, and we don't have to move that back on the camera. We don't have to snake the wires for the switch because the switch is already pushed through the board. You will want to glue the switch into place. Right now, it's stuck into the board. It's stuck into the base just because it's a bit of a tight fit. So you could leave it like that, but eventually the plastic will wear and it will slip out. So I'm going to put some super glue or some hot glue along the inside of this to keep it steady. You want to be careful about super gluing these things because if the super glue gets inside the switch housing, it'll gum it up and you have the potential to ruin your switch. But yeah. So we're going to solder. The first thing we're going to do is solder the surface mount piece onto the wires we have snaked through. I'm snaking them all. I'm pulling them all the way through. You've got a couple of inches of slack here. But yeah, the important thing is to make sure you're paying attention you want to compare, make sure that these are going to the right wires. So we've already verified that the red wire connects to the positive lead on the inside. So I'm going to line this up. I'm going to put this back on the microscope first. All right, so we've already verified that the red wire inside goes to the positive lead. So I'm going to connect this to V-bus. Same way, I'm going to heat my soldering iron back up while I'm twisting my wires here a bit. All right, so V-bus goes, the red wire goes to the V-bus hole. Just twisting that back around so it stays put. And then I'm going to get a little bit more slack on my ground wire. All right. I'm going to give that a twist. All right. I'm just going to look inside here and verify that we're doing this right again. And I'm comparing it to my existing known working example of this. And the wiring is good. And, you know, if you make a mistake here and you accidentally solder the ground wire to the V-bus pin or the 5-volt pin, you know, it's not the end of the deal, end of the world. You can definitely cut the wires and resolder them again. You just want to kind of try to avoid making mistakes the first time if you can. And my wire came loose, so I got to stick it back in here. When you're sticking the wires through the holes like this, you want to make sure you don't have any of the fibers of the wires running astray. You want to make sure they're all going through. The reason for that is because these wires are made up of little fibers, and if you've got one fiber from this hole bridging to this other hole, it can cause a short circuit. So you could damage your devices, or it won't work. So just, you know, be careful. Again, check twice, solder once. All right, so that's looking good. I'm going to place, it wants to flip over. That's great. I'm going to try to get this to cooperate here. All right, I'm going to get my trusty piece of electrical tape and get this back into frame. And just stick this here so that it can't flip back over. And yeah, just verifying that the wiring looks good. That we're all the way poked through the holes. Yeah, all right, cool. Soldering iron is good to go. I'm going to flux this stuff up. One for the ground pin, one for the 5-volt pin. Got the soldering iron. Get my bead. Solder. One for the ground pin. And one for the 5-volt pin. Those look good. See, it's nice and flat. Nothing weird poking out. All right. So, easy peasy. So we're going to pull the slack back in. And then just mount it. It's out of frame, sorry. Pull the slack back in and just mount it like that. Hot glue, super glue, whatever glue you like. For now, I'm just going to tape it down because I don't have my glue gun heated up. So I'm just going to tape it down to the base like this, just so it stays put, like so. And you can see the solder joints look good. We've got a little bit of excess wire here that I need to trim. Again, not strictly necessary. You can see the little bit of excess wire here. It's not strictly necessary to clean this up, but being a perfectionist on these things will save you some time. Uh, Nothing's going to come into contact there, but depending on what you're putting on top of this base, if you're putting metal stuff on top of this base and you've got wires sticking out and you don't insulate all this properly, you can cause a short circuit. So we want to just clean stuff up because it's real quick, doesn't take much time. All right, so we got our surface mount wired up. That's on there. I'll go back later and hot glue this. The next step is to wire our switch. Let me get this in frame here. All right, so this is the switch. These are the terminals on the bottom of the switch. The switch has two positions, off and on. There's three pins on this. We're only going to use two of them. The ground pin is the center one, and we're going to put 5 volts, or we're going to put the enable pin wire here. So when the switch is off, like it's in its current position, the middle and this pin are connected. When the switch is on, this pin and this pin are connected. On and off. I mean, there's no this switch. This position isn't on. It's just one of two positions. So you can like switch like that. There's no preset on or off. It just depends on how you wire it up. So really, we're just going to connect the ground here and enable here, and it'll work. So let me get my wires snipped real quick. And I'm going to give myself a little bit more slack than normal because these are snaking through the pins on the switch, which are a little bit more awkward than the. All right, let me switch this to the bench cam. It'll be a little bit. Well, maybe not. Okay, so it really doesn't matter how you wire this up. You can't screw it up as long as one of the wires goes to the middle pin and the other one goes to one of the outer pins. You don't want to have one connected here and one connected here because then you'll never be able to make the circuit. So I'm just going to connect one of these pins to the center. Twist this so it's a single thread. Just kind of bend it in so it stays put. All right, so that wire is going there, and you want to make sure that that you do these one at a time, and that there's no, so that you don't accidentally solder a fiber from this wire to this pin. Let's pinch that on there. This can be a bit tricky because you don't have the holes from the circuit board to solder into it, so it kind of jumps around a little bit. So I'm gonna put some flux on here, and then I'm gonna solder this wire first, and then I'm gonna inspect it to make sure it's not bridging. Because if the wires bridge from one pin to the other unintentionally, it'll be a short circuit, and it won't work, or it'll stay off or always on. The switch won't work. So, all right, so it's flux on there. Getting some solder in my iron off camera. All right, so sure this is on camera. We're making sure there's no bridging between the pins. And just make sure, double check that your solder joints are strong here, because it's a little bit more difficult to solder on these switches than it is through the vias on a board, because the holes are a little bit different. So this one looks good. There's no extraneous fibers flying off, and it's in there good. Okay, so I'm going to take this other wire and stick it through one of the other pins on the switch. All right, that's good and neat. It's not touching anything else. Just gonna make sure that's secure. Put a little drop of flux there so the solder runs. All right. And yeah, this is going to be probably our last solder joint, so hooray for that. Clean the solder iron up a bit. So, just really make sure it's on there. That's important. You don't want these wires jangling around because it might make it so that it turns on and off by its own, and that's not good. Okay, so these soldering joints look pretty solid. I'm just going to check to make sure the wires are in there good and not flopping around. Yeah, that looks pretty solid. So now we've got, switch back to overhead, or there you go. So we got a base. I'm gonna heat my glue gun up so we can secure these pieces here, and then that's pretty much it. Plug my Dremel, plug the glue gun in, and I'm gonna break these videos into segments. This part is just how we're wiring up like the microcontroller and the power system in the base. We're building the base. Once you have these bases with this design, you can put anything you want on top of it. I've got these armigers over here that do the robotics movement. I've got one that just has like a 3D printed it's like half of a 3D printed armiger out of clear resin that has 1 million LEDs in it, and it's all controlled by the same microcontroller. It looks really cool. It's like a rave armature. But okay, so let's get this base finished up and the microcontroller wired in, which is the next step. So I'm going to peel the tape away that was holding that in place. And I'm going to give this a minute to heat up. Switch to overhead again. Okay. Or bench. There we go. So we just want, the key here is just to have this on here securely, because this is going to have cable insertion stress on it. So when you need this to be in there pretty good. I use super glue for these sometimes, but I'm going to use hot glue for this one. And you want to use a good pad of hot glue just to press this down hard to make sure it's got a lot of surface contact. All right, I'm going to fold this up. Good bit of hot glue down there, and just smush it down. Make sure you don't have hot glue going into your micro port or USB port. Just gonna put some pressure on that until this cools. Hot glue cools very, very quickly, so you don't need to worry about holding it like super glue. It sets within seconds. Make sure it's on there good. You might want to, you can see some screw holes here. You might want to consider screwing this down if you're finding that the glue is coming loose. So I'm going to trim the little bit off the glue that kind of overhang. And yeah, this is on there solid. That's good. I'm going to do the same thing on the underside of the switch here. I'm just going to put a little bit of glue on either side so that it stays put. We don't want this popping out, because right now this is just in here by pressure. So, oh God, come on. Let's get this excess glue off the end of this thing. Hot glue is good and bad. It's a mess, but it holds pretty well, and it's semi-permanent. So we're going to put a little bit of glue here, smear that stuff on there. Do it for the other side. Try not to burn your wires, because this is hot enough to do that. Yeah, easy. All right, that's done. Let's give that a second. I'm going to pull the hot glue out. Actually, I'm going to leave that plugged in. I want to use that later for the microcontroller. All right. So the result is Actually, while I've got the hot glue gun heated up, I'm going to put a bead here on both of these wires where they enter the base so that the stress doesn't pull the solder joints. There shouldn't necessarily be a lot of stress there, but you just want to idiot-proof this thing so in case it gets knocked or yanked or something, it doesn't pull the wires out. And you'll notice when you hot glue, you've got these glue fibers all over the place. Just, ball them up and clean them out. You'll have this crap all over. Just clean it off. You don't want to leave it in there because it'll just crap up your model, especially when you've got like moving parts. Having that glue work its way into your servos is not great. So just cleaning up all the bits to make sure this is clean, all the wire cuttings. The result should look something like this. You've got your solder joints on the switch that are good. You can put some electrical tape over there. That's probably not a bad idea. I'll go ahead and do that now. Doing that makes sure that if you've got something in the board, like if you've got additional components down here, they don't accidentally touch the terminals on the switch, causing a short circuit. Just a little bit of electric tape. You don't need to use too much of this stuff. And you don't need to lay this stuff flat either because it stretches. And you just kind of smush that up on there so it covers. It doesn't need to be like a seal. It just needs to cover. This stuff will stick to just about anything. So you can see it's not the most beautiful thing in the world, but it prevents stuff from contacting the metal under there and causing a short. So you just want to make sure that all the wiring and everything fits nicely inside there. And yeah, you can see got a very nice setup here. Switch, make sure the switch runs properly. And so yeah, now we got to test to make sure this thing works with the battery. Make sure all of our wiring is indeed good. Hopefully this doesn't turn into a troubleshooting video in just a second here. So I'm gonna take the battery, I'm gonna reconnect it inside here to the charge port. Got our little blue light, that's good. So, all right, so I'm gonna make sure you can see this. Little blue light, that means we've got power coming in from the battery. That's not good. Oh, hold on. No, that means the power is outputting over these wires here. So when we turn the switch, that light goes out, which means the switch is the device is now off. Turn it back on, the device is now on. So this is good. Everything's looking great. No short circuits. So now that this is the power system, it's complete. I'm just going to arrange the battery so there's less stress on the wiring. Okay, our power system is complete. From this point, we can build a robot. We've got all the power that we need. We've got the microcontroller. Like I said, if we remember from the beginning of this video, the microcontroller has a 3V pin on it, which is where we're going to get our 3-volt power because it has a regulator built on. So the next step here, and the last step really, is to attach the microcontroller to this setup. So let's do that. Okay, so the way I like doing this is I want to basically just hot glue the microcontroller onto the board, or onto the underside of the Games Workshop black base. So I want to kind of stick this on here and get an idea of where we're aligning this. You can stick the microcontroller over the battery. There's plenty of clearance here in the way this base is designed. So in our setup here, we're going to want to put the microcontroller kind of right here. Just, it really doesn't matter where you want it. You just don't want to have it directly over the power converter because of the heat. So I'm going to aim to put it like right here. So if we flip this back over, putting it kind of right here. So the first thing I'm going to do is I'm going to mock this up. Stick that there. I'm going to connect the power from the the converter to the microcontroller, and I'm going to make sure everything is happy when we flip that switch on. Okay, so got the microcontroller hooked up. I'm going to make sure that its little light turns on and that it's happy when we flip that switch. Hopefully that no smoke will come out. And come on, switch. We are happy. The little pixel, the little NeoPixel on the microcontroller is doing its pulse thing, meaning it has no code running on it because we haven't put any on there yet. That is great. I'm happy about that. I'm going to turn this off. I'm going to disconnect this because I don't want to be hot gluing on a potentially live circuit. It's not harmful. It just, you never know. It's always good to just be safe. You're not dealing with enough voltage here to be harmful to you, but you can absolutely damage some of the stuff you're working on. All right, so the thing you'll notice on the bottom of this microcontroller is a microchip. That is your CPU. You can glue onto the CPU. This shouldn't ever generate enough heat to melt the glue, but you don't want to touch your glue gun tip to the CPU. So what I'm going to do is I'm going to add some glue to the bottom of the base where I'm going to stick this thing on, a nice generous pat of glue, and then I'm going to stick this chip right on here, or the microcontroller. You got to put some pressure on it so it bonds well. And this might take a couple of tries to get this to really stick on there. It's not the best way to do it, but there's no other way because there's not screw mounting holes on the microcontroller. And just make sure that's nice and sturdy. And yeah, that's on there good. So I'm gonna stick the power jack right back on there. There. So that's what that looks like. We can see that we've got our circuit pretty solid, and we kind of want to have it aligned. You know, we got to shove these wires down to get them to fit, but just verify that this is on right. And you can orient it any way you want, just as long as the microcontroller isn't directly over the power converter, because you don't want the heat from the power converter influencing the microcontroller or cooking it. And in this case, the microcontroller is right here, which is directly over the battery. And if you kind of look inside here a little bit, you can see, not really well, but there's about 5 or 10 millimeters of clearance between the battery and the microcontroller. And that's great. So that's our base. This is pretty much the way this is going to look. The Armiger is going to stand right on top of this. I'm going to look inside one more time and turn it on to make sure the microcontroller's happy. Everything's looking awesome. You can see inside we've got lights on both the booster board and it's the strobing light on the microcontroller. So we're good to go. Turn that off. And you know, the other thing you can do here is once you figure out where you want all of your mounting to go, you can just add a little bead of hot glue to these to lock these wires down a little bit better. Not necessary, but just keeps things clean. So, and also what you can do is to seal this in to keep the base on, you can add magnets here. That's what I've done with my other robots. Or you can screw it down, or you can glue it down. I would not recommend adding magnets or glue or anything until you're done with the robot and it's programmed. Because in order to program this, what you do is you remove the power connector from the microcontroller and then use a USB-C cable to connect this directly to your computer. And I'll show you how to program this later on another video. But you don't want to seal this in before you've programmed it. Otherwise, you'll have to break the seal. And just leave this nice and loose until you're ready to go. But yeah, that is the base. This is a complete power system. This will supply via the microcontroller 3 volts for your robot, 5 volts for your robot. You've got your on and off switch. You've got a charge port here that you can use to charge the battery without cracking open the base. Everything's solid. You know, these things play really well on the table. They add about 18 millimeters to the height of the robot or height of the model. You know, these things are never going to be tournament legal. but they're great for casual games. So yeah, and once this is all buttoned up, you can paint this. Just make sure when you paint it, you mask up the switch a little bit so you don't get paint down in there. And also the same thing for your micro USB port. Just put some tape over here when you're spraying or painting. And yeah, that is it. You've got a working base. I've mass produced these things. Like I built 3 or 4 of them for my other robots. Uh, you can see the design is exactly the same for my robots here. So yeah, and you flip the power switch back here, and yeah, he starts dancing. So this is a we're gonna build something like this, but with one servo and some LEDs. This one's very complex. It's got lasers, it's got voltage converters. It's just ridiculous. It's got 3 servos. Not a good first project, but you can use the principles that we're building with this base to power something like this. So, let me make sure I'm not forgetting anything else. I think we're good. Um, we've tested, we've verified, everything's working good. I'm going to call it a night. Uh, I'll get this uploaded on YouTube with all of the STLs for the base linked, all the part numbers for all the pieces I've used here linked up. Um, yeah, I hope anyone watching the VOD gets a good information out of this and how to build these things. And please don't hesitate to contact me, DM me, whatever you need, whatever you need to do. I'd be happy to help you do these things. Um, please don't ask me to do commissions. I'm not doing those for a number of reasons, legal and legally. I don't want to be responsible if somebody builds one of these things and burns themselves in the building, or if they damage the battery and it explodes. That's on you. This assumes that you've got some basic understanding of how electronics work. Please don't freehand this. Like, don't make sure you know the basics of what you're doing, especially when you're dealing with a LiPo battery. We do not want to turn this into a grenade. So, a good way to practice soldering is to just find some broken electronics, get a soldering iron and just solder stuff onto the broken circuit board. That's good. There's plenty of YouTube videos to show how to solder, but yeah, I would recommend getting some practice before trying something like this, but it's not too much practice. You don't need too much practice. But yeah, the next video will cover how to wire up the servos. I'll probably be putting some legs on this platform with a hip joint that contains the servo, and also I'll show you how to set up the all of the slip joint, the ring bearing stuff that you need in order to put this together in a way that's not going to cause friction. But that'll be the next video. For now, we've got our base. We're ready to go. Power's looking good. Computer's looking good. We can start programming this if we wanted to, but we've got nothing to show the programming. So I'm going to wait to do that in a later video. Yeah, let me know if you got any questions. I'll try to get everything linked up with the parts list once I post this on YouTube. Until then, I'll see you later.